welcome to the latest in these EdgeFirst Studio workflow tutorial videos. In this video, we'll be showing in two parts. So in the first part, we'll be showing model training, and in the second part, model validation. So for model training, we'll be showing the Ravin indoor dataset. We'll go over some quick details of this dataset, and then we'll show how to train the Fusion model, including doing a little test comparing different image resolutions as an example. And then in the second part of the video, or in the separate second video, sorry, we'll be doing the validation, where we take the quantized model, show how it compares to the floating point model, that we're not losing any significant accuracy by quantizing, and then deploying to the Ravin. So let's get started. We've got the Ravin indoor dataset here. It's about 22,000 samples, so on the small size, but serves as a good example for this. It trains pretty fast, takes about 90 minutes, and we'll be going over that. So just a quick recap on this dataset. It's trained on mostly indoor, all with the radar in ultra short range mode. What that means is the radar is good to 9 meters maximum, and we're set up to detect people to about 8 meters. So here's some examples of it. We do have some outdoor scenes around these shipping containers, around the tractor over here. So a good example video, our data set. So first, click the menu item here where we can select all the different sections of DeepView Enterprise, and we're going to select the trainer. So when you first go here, you'll get this this blank screen. Now, the way the trainers are managed is under experiments. So you create an experiment, and within the experiment, you can run multiple training sessions. Experiments themselves are a bit abstract. This is mostly for organizational, so the user can use it however you wish. Typically, what we would recommend is you create an experiment for different parameters you want to investigate, then run a bunch of training on those different parameter configurations within an experiment that's named accordingly. So in this case, we'll demonstrate training at different camera resolutions, and then so there'll be different training sessions. So without further ado, we'll go create a new experiment, and we'll call it camera size testing. Sorry. Okay, and then experiment various camera resolutions. There we go. So I create this experiment. There we go. There's no sessions created. So we'll be able to compare charts that show different results across the different experiments. So we'll create a new session. So I'll go into a little bit more details of the parameters the first time, and then I'll just create the other training sessions afterwards. So first of all, trainer type. What this means is selecting which type of model we want to train. So by default here we see model pack. This is a vision only model that can be trained to detect basically bounding boxes and segmentation masks. So we've seen examples of that before, so we use this model for that. For this demo, we'll be training the EdgeFirst Fusion model. So this is a model that's consumes camera and radar data, fuses them together, and then generates an occupancy grid, which is basically the spatial location of the target objects. So when we say an occupancy grid, it's measured in meters. So somebody's 2 meters away from the camera and 1 meter to the left, for example. So that's the EdgeFirst Fusion. Name and description we'll come back to after, the self-explanatory. From dataset, so in this case we just have the one dataset that we've opened up, the Ravin indoor, and then annotation set, again, we just have the one annotation set. Where you would have additional annotation sets is we've shown examples of doing the automated ground truth generation. So this imports into this annotations. Then you would typically do an audit to ensure that there's no errors. While auditing, just as good practice, we audit into a new annotation set, which would be called, for example, audited. And then you can compare, the two data sets and measure effectively the accuracy of the automated ground truth generation with respect to the audited one. But here we just have this one example. Okay, now for the model settings, they're broken down into model input parameters, model output parameters, model parameters, so for the backbone, and then general training parameters. On the input parameters, the first one is camera. So we can, choose to enable or not the camera input. The Fusion model supports training with camera only, radar only, or the fused camera and radar, which is the default and preferred, but you can do comparisons where if you want to see how the system works on only camera or only radar, we can do all these types of experiments here. For camera, we can pick different resolutions. So by default, we've got these resolutions defined that are all using the 16:9 aspect ratio of the camera. Camera filters, so this is on the first input, how many filters or how many feature maps we generate on the first layer. Radar, again, same thing, can enable, disable. We have two radar modules supported, the drive grid 169 and 171. In another video, we'll use the 171 to demonstrate other aspects of the radar data cube and how it compares to the 169. But for now, we're using the 169. Range modes, so the radar module itself can operate at different range modes. There's trade-offs. Basically, the shorter the range, the higher the resolution it's capable of providing, but it doesn't see as far. So in this case, this data set was for indoor applications for which the ultra short range works what we find the best. We're detecting people, typically not even going that far. Like if you think of a trade show type application, people are rarely going to be more than 5 meters away. Radar sequence, this relates to the radar data cube. It generates for every sample, there's two sequences. One where only one transmitter is running, that's the A sequence, and one where all transmitters are running at the same time, and that's the B sequence. We'll explore in another video the data cube in more detail and how that looks and why that's important. But for now, typically as default, we just want the B sequence. Again, radar filters, same as the camera filters, it's just how many feature maps are generated on the first layer. Typically do about 2 times more on the radar compared to the camera, just because there's more natural features to the radar sequence. There's, in the case of the 169, we have 4 receivers. Each one of those is a channel, and then the data is represented in complex, which we split into separate feature maps. So we're just dealing with normal values, real values. Right, so 64 radar filters. Next, moving on to output parameters. So the detection range scale, this is meant to be used with respect to the radar. When the radar range mode is selected, so say 9 meters, or for the longer ranges, we've got 19 for short, 56 for medium, 130 for long. That refers to how far the radar, or how many meters the radar can represent, not necessarily how far it can see a given object. So a train, it's going to be able to see that at the maximum range. Heavy equipment should be able to see that at the maximum range. But people, not so much. So in ultra short range mode, it's so short that typically it's seeing people everywhere in that range. But as we go to the short, medium, and long range mode, we find that about half of that, or really a bit more, like 3/5, is the maximum where it can see an object such as people. So the default is 50%, but again, in this case, in ultra short range mode, we can detect people at most of the range. So we'll set this to 90%, which will mean an occupancy grid of about 8 meters. Occupancy grid scaling. So the occupancy grid is naturally represented in meters. So each cell represents 1 meter. But if we want higher resolution on the output, on the localization of objects, that's what the occupancy grid scaling does. So it works at basically 2x, 4x, or 8x. And what that means, it's a multiplier on the resolution within the cells. Another way to look at it is you divide the cell. So at 2x, we divide the cell by 2. So instead of having 1 meter resolution, we have 50 centimeter resolution, and then 25, and so on. This happens later in the model where it's fine-tuning the predictions through this grid scaling. Output filters. This is for the BEV, or bird's eye view decoder, as part of the occupancy grid. So it uses 64 filters to start, and then expands them as it goes through, actually contracts them as it goes through. The backbone, these filters get expanded as it goes through. So for each block, the filters are doubled and the spatial resolution is cut in half. By default, we have 5 backbone blocks. Each block has about 4 convolutions. So we can scale this, to be a shallower or deeper model. For deeper models, basically you need a bigger data set. This is still small scale data set. It's only 20,000 samples. It's good for demonstration, good for indoor demos, but as you expand to hundreds of thousands and millions of samples, you'll be able to support larger models that provide better accuracy. Epochs and batch size. Batch size affects, as we're processing the data set during training, how many samples are presented to the model at any given time. Bigger batch size means we're able to better leverage the GPU. It does limit memory usage, so you can't be too big. And there's also some trade-offs at training where really large batch sizes become a bit trickier to deal with. We'll leave it at the default 32 for this, but it is a parameter that can be tweaked. Epochs counts the number of iterations into the data set. So here we'll do 50 iterations on the data set. Again, small data set, smaller model, there's no benefit to going further, but some models, certainly as their data set grows, there's benefit to training for longer time, so that can be scaled up. Okay, so I mentioned we would do a little comparison of input size. Basically what we hope to show, because it's ultra short range mode, we're only detecting people to about 8 meters, that the camera input resolution is not too important. So we'll see the accuracy does vary with input size, but and then we'll also show the performance on the device, how higher input size does require more computation, and it's all a bit of a balancing act. So for now, we'll say this model is, the name, we'll just say it camera 320 by 180. And then we'll go ahead and start the training session. Now this takes a little while. It'll initialize the server where the training's performed, download the files, do the actual training. In this case, I believe this data set's roughly 90 minutes to train the model. And it goes up and down depending on the size of the model. Now, what's nice, so as you see, it's creating a server for this. We can create any number of these. So we'll create 3 to show 3 different resolutions and the results. So we can go ahead and just click create new session. I'll go through this a little bit quicker this time since we've already talked about the parameters. I'll pick the next resolution and I'll say camera 40 by 270. And I'll kick that off. And then again, I'll create another new session, next resolution. And this is camera 640 by 360. Then ultra short. I think I forgot to do this on the other one, so I'll stop it and go change these parameters. So 95. Okay, it's good to go. Yeah, so this one here, I used the wrong value, so I'll just stop it. All right, new session. Ultra short. Okay. So now we have our three model training sessions running. We'll speed up the video, skip ahead 90 minutes to see the results, but while it's training, while we speed it up, you will see the loss function will start the graph when it's actually training. We can open up, well, there's no charts yet, but this will be populated with all the charts. We'll just go look at them after. We'll be able to do some comparisons and whatnot. We can see the parameters that we picked here: confirm, right, ultra short. We see the system log, so it's starting up the training session right now. So that's what we're seeing here. And then yeah, so we'll speed it up, and then we'll meet back again once that all three training sessions complete. While these continue training, slowing down the video here to go over a couple points. So I mentioned the loss gets plotted here while training's happening. So we see these graphs updating for all the models as they go through. But now that we are generating these data points, these happen at the end of each epoch. So we can see 15, 19, and 11 epochs of progress. So if you click this button here, this brings up the charts for this. Now these will update in real time as it's training, but it's showing you the training charts for one model. But this gives us a breakdown of the metrics we collect at training time. As we'll see in part 2 of this video, there's many more metrics that we use during validation that give us more insights into how the model is performing. But these are sort of the common general representative benchmarks or metrics, while training. So they're split between basically the training metrics and test metrics. So those with test underscore, IOU, precision recall, those are the metrics collected against the small validation subset. So the split we've done for the indoor data set, we didn't go over that at the beginning, but we'll see, we'll add a little overlay here to show it, but there's, of the 22,000 samples, we've split it as 20,000 for training and 2,000 roughly for the validation. So basically, test IOU is the IOU, so the intersect over union measurement over the validation data set. But this is still from our training model. So we're training the model floating point under the hood. In this case, it's using Keras for the implementation. So that's the model that's being validated here. When we do validation later on, that's going to be using the quantized model that runs on the device. We'll also do a comparison where we validate the Keras model, so we can kind of see, what what happens when you quantize. Basically, there's a small loss in accuracy. So these charts, so again, IOU, the intersect over union, there's two sort of versions of this metric. One's with respect to detection models, and the other one for segmentation models. The occupancy grid model for these metrics we treat as a segmentation problem. So basically, each cell is like a pixel, and the pixel can be any given class for the object in that cell. So that's what we measure with these metrics. So basically, if your prediction for a given cell is correct, then that's a true positive. If you predicted, a person where there's no person, then that's a false positive. Or if there was a person in the ground truth and you missed it, then that'd be a false negative. And these metrics are used to generate the precision, recall, and IOU. So we'll see, it's still a bit early in the training, but again, with this smaller data set, only 20,000 samples, you'll see the training metrics actually, they're basically perfect. And that's why we don't want to train the model more. It'll quickly overfit on this. So we see our precision, is 95%. It's approaching. It'll finish at very near 100%. Same with recall. On the test precision and recall, it'll be a bit lower. It gets into the 80% range. So that showing this updating as training is happening, and we can look at these. For all of these. So this one is only at epoch 16. So if I open that up, we see the numbers. Again, it hasn't trained as much, so precision and recall aren't quite as high as that other model. But again, they will end up very high at the end of training. So with that, we'll go back into fast forward mode and review the results once training is done for all three models. So now training the three models is completed. As we see, each took about an hour. I guess 90 minutes was a bit high. So it's about 60 minutes. It varies. Larger models a bit, take a little bit longer than the smaller model. But they all run in parallel. And that's one of the, key things of being able to train under such a platform is we can spin up as many training sessions as we want in parallel and then look at the results without having to wait, for them to all run serially. Okay, so we had looked at these charts before. Now we can see the final results. So we see that test recall in the end was here was about 76%, and then their test precision was about 79%. Now, looking at each one of these is not the most effective way to compare. So what we can actually do, we can click this here, and this will open up all the charts so that we can compare them between the various training experiments. So we see they're all overlaid onto each other like this. So we can see at a glance, the TEB session seemed to have had the highest test precision, test recall, test IOU. It's clearly at the top of all of those. Now if we go back, we can see TEB was our 480 by 270. So overall, this one produced the best results. And again, 8 meters, the higher camera resolution's not really adding a lot. The radar was the same setup for all three cases. And we know the radar is able to make detections of people even when the camera's occluded. When we look at validation, so the actual quantized model running on device, we'll also be able to get timing differences where we'll see, obviously the 640 by 360 will be the slowest of the three. It's just it needs to process more pixels. But yeah, that shows that. Now we can download the models as well. So if we open this to get more details, it shows the training logs, model parameters, and on the right side here we have our two models. So during training it generates this Keras model. This is quite large, really only relevant for training. You can download it if you want to do some testing on a PC or whatnot. But for running on the embedded device, we want to grab this quantized Fusion TF Lite model. So if I click this, it'll download, and then I'll just quickly show using Netron. So Netron.app is a common tool for visualizing models. So if I click Open Model, I can select the Fusion model that I just downloaded, and now we can see, the 480 by 270 input resolution of the camera, the radar, and this was based on the range configuration, but it has 200 range bins, 128 Doppler bins, and 8 channels. So as I noted earlier, the radar data is complex 16-bit, so there's a real and an imaginary counterpart, and then there's 4 receive antennas. So and each one of those is a 200 range by 128 Doppler bin matrix. So the arrangement that we use for the Fusion model is to split the real and imaginary parts into separate channels that are just normal real numbers, and that way it works nicely with the rest of the model. So real and imaginary is 2 times the 4 receive, and that gives us those 8 channels. And because of these more channels is why we picked a larger filter bank at the beginning, so the 64 filter bank, compared to the camera, which was using 32 filter banks at the beginning. So now with these inputs, each backbone runs in parallel to do all the initial processing of the data, and then eventually we get into the Fusion preparation portion of the model, the actual concatenation of the two inputs together, further convolutions fusing the data together, and then finally our occupancy grid convolutions, which in this case we weren't using the sub-meter scaling, so it's outputting a 8 by 16 meter occupancy grid. So the range is 8 meters, and then as well, so 8 meters, from the Ravin platform out, and then 8 meters to the left and right gives us this 8 by 16 meters. There's a portion of it that's invisible to the camera and radar, but for the occupancy grid, that's ignored. We'll see when we go into validation details how we can actually observe the visible range, where we have ground truth annotations, where the model performs well or poorly around the extremities of that visible range. But with that concludes the training portion of the video. We trained these 3 examples using different resolutions. We saw that they're effectively, the same, very close results between the 3, and we are running at a very short range, just 8 meters. In the next part of the video, we'll be going over more detailed validation, visualizing what the actual occupancy grids look like, and validating the model on the device to also collect timing information and what the drop in accuracy from quantizing from floating point to 8-bit integer. In future videos, we'll then also show running the model on the device, doing some further timing analysis and whatnot. And this all feeds into this loop where that model is running on the device. When recording, we can collect the predictions that the model's generating, Again, we bring in these MCAPs back into DeepView Enterprise and continue the cycle of improving the data set, further improving the model, and then eventually getting to a very robust solution. That's it for this video. Thanks for watching.